urinary system. So last time we were talking about this guy right here, the glomerulus, the site of filtration. We know that we want to filter about 125 milliliters per minute. I mean, that's how much filtrate we want to make every minute. Too much, and filtrate moves too fast, we don't reabsorb good stuff. If it's too little, filtrate moves too slowly, we reabsorb bad stuff. So in order to maintain that filtration rate in here, we got to maintain blood pressure in here. Okay, so if blood pressure drops in the body, well, it makes sense. Blood pressure will drop in the glomerulus too, and that's not good. In order to offset that, the afferent arteriole will dilate. That'll bring more blood in, which will bring the blood pressure here back up to the normal value, around 60 millimeters of mercury, that we need. It's called the myogenic mechanism. Myo, muscle, genic, created by. So created by muscle. And because it's a smooth muscle in here that's doing the vasodilation. All right, and you probably could figure this out on your own, but if blood pressure rises, well, I mean, we don't want it to rise here. So to deal with that, to counteract that, the afferent arteriole is going to vasoconstrict. So blood pressure goes up, this arteriole vasoconstricts, less blood gets in, which brings the pressure here back down to the normal that we need. All right. The myogenic mechanism is one way that we maintain glomerular filtration rate. Another way is the tubuloglomerular mechanism. All right, let's start at the glomerulus right here. Let's suppose we are filtering too slowly. All right, so filtrate flows slowly. As it flows slowly, there's more time for reabsorption. So by the time we get all the way to the distal convoluted tubule, there is less sodium chloride in the filtrate. This is going to be recognized by a group of cells collectively called the macula densa. They're going to tell the afferent arteriole, hey, don't constrict so much, which is going to make it dilate, which is going to make more blood rush in here, which is going to bring the blood pressure and the glomerular filtration rate both up. All right, wonderful. Now we're done with maintaining glomerular blood pressure and glomerular filtration rate. And we got to talk about some other things that can affect it, including the sympathetic nervous system. In the case of increased sympathetic activity, the copious amounts of norepinephrine and epinephrine that are going to be released are going to cause the afferent arteriole to constrict. That's going to make glomerular blood pressure and glomerular filtration rate go down. The advantage of this is it maintains blood volume. All right, because we're not making as much filtrate, we're keeping blood volume up, thus keeping blood pressure up, which we need in order to drive blood flow as we try and escape from whatever reptilian monster is trying to attack us. All right, and since we're speaking about blood pressure, it would be remiss of us to not talk about the renin-angiotensin system. The renin-angiotensin system. So here's the deal. Suppose blood pressure drops, or you get into a fight or flight situation. In either of those situations, cells known as JG cells, JG stands for juxtaglomerular, which means next to the glomerulus, they release renin into the blood. Renin is going to act on a plasma protein. It's always floating around in your blood. It's called angiotensinogen. It's made by the liver. You know that the ogen at the end of a word often indicates that it is an inactive form. We saw that with pepsinogen. We saw that with fibrinogen. Now we see it with angiotensinogen. And renin converts angiotensinogen into a moderately active chemical called angiotensin 1. So now in the bloodstream we got this moderately active chemical called angiotensin 1. But it's not strong enough. So what happens is angiotensin 1 is going to be converted into a much stronger, more potent chemical called angiotensin 2. And this conversion happens in the lungs primarily because the lungs make an enzyme called the angiotensin converting enzyme. Okay, so now we got this powerful compound in our blood called angiotensin 2. Now, angio means vessels. Tensin, obviously, has the idea of muscle tension, contraction. So, no surprise, angiotensin 2 is a vasoconstrictor, which increases TPR, total peripheral resistance, which increases blood pressure. All right, meanwhile, angiotensin 2 tells the cortex of the adrenal gland to release aldosterone and tells the posterior pituitary gland to release antidiuretic hormone. Both these guys increase your water reabsorption in your kidney, so getting more water back from filtrate. Meanwhile, angiotensin 2 makes your distal convoluted tubule do more reabsorption of sodium, and osmotically, that's going to cause you to reabsorb more water. Plus, it makes you thirsty. Thirsty you are, the more you drink. So you're stealing more water from pee, you're drinking more. That combo yields an increased blood volume, which, of course, corresponds to a rise in blood pressure. Okie dokie. Speaking of reabsorption, look at that segue. That was a great segue, wasn't it? Speaking of reabsorption, we got to talk about reabsorption in the PCT. In the PCT, generally, quote unquote, good stuff needs to be reabsorbed. And by good stuff, we mean water, nutrients, vitamins, electrolytes. Reabsorbed molecules are going to take route 2 right here, boom, boom, from the proximal convoluted tubule to the peritubular capillary. And one of the most important things we are going to reabsorb is sodium chloride. You'll see why. All right, check it out. Here's my process of reabsorption. Got my filtrate in the lumen of my PCT. Here are the cells lining the PCT. Check out these microvilli right here to enhance surface area. All right, so water and solutes, they can either go through the cell, transcellular route, into the interstitial fluid, into the blood, or they can sneak between the cells, it's paracellular route, again into interstitial fluid, into the blood. Harder to do this paracellular route because these little purple things here represent tight junctions, and in general they impede that sort of flow. Transcellular route, in my opinion, is better because it's more easily regulated. We can regulate very easily what goes through cells, depending on what receptors and proteins and channels we have in here. It's harder to regulate what goes between cells. All right, let's look at some stuff here. Here, oh, check it out, sodium. He's our favorite right there. Sodium is abundant in the filtrate, not so abundant in the PCT cell. So sodium goes down its concentration gradient from the filtrate, where it's abundant, into the cell where it's less abundant. This downhill motion of sodium is going to drag other things with it. The downhill motion of sodium is going to provide the energy. This is good old secondary active transport, which you might have remembered from AMP1. And then energy from the downhill movement of sodium is going to drag nutrients, glucose, amino acids, some ions, some vitamins along with it. All right. Then those nutrients amino acids can be shuttled out the other end into the blood. Meanwhile, check out our old friend here, the sodium-potassium pump. Moving 3 sodiums this way, 2 potassiums that way. This makes sure the sodium concentration inside the tubule cell is low, which is going to allow this to take place. All right, meanwhile, this movement of sodium is going to osmotically cause water to take the same path. Through its aquaporins here, its water channels, water is going to go the same way. This is obligatory water reabsorption because you're obliged to do it. It's obligatory. You got to do it. Meanwhile, lipid-soluble substances, whoosh, zip right through. Some other stuff, chloride, calcium, potassium ions, are going to try and slip through the paracellular route. All right, we could go into a lot more detail here, or not. Sorry about that. All right, see you later.